All right, why are some things radioactive? The answer has to do with physics. The particles in the nucleus are held together by something called the strong force. It acts only over very short distances. And the neutrons play an important role in stabilizing the nucleus as they add to the strong force but don't repel each other like the protons do. So that ratio of neutron to proton is a measure of stability in the nucleus. If the ratio is too high, neutrons are converted to protons via beta decay. If the ratio is too low, protons are converted to neutrons via positron emission or electron capture, or by alpha decay. So there's something called the valley of stability. You can see in yellow there is the valley of stability, and those are the stable nuclei. So if your atomic number is 1 to 20, you want about a 1-to-1 ratio of neutrons to protons. For 20 to 40, you can see we start to curve up here. That ratio approaches 1.25. For 40 to 80, we're even steeper. It's about 1.5. But then once we get above 83, nothing is stable. That strong force, it can't be balanced out. Okay, so using this valley of stability, we can predict things. So predict the kind of radioactive decay that magnesium-22 undergoes. Well, magnesium's element number 12. So 12 protons. We can take the atomic mass, subtract the protons, and get the number of neutrons. Then if we take our neutrons divided by our protons, we get a 0.83. And from elements number 1 through 20, we want a ratio of about 1. So we don't have enough neutrons. So if we convert one proton to a neutron, then we'll be at that 1-to-1 ratio. And it can do that via positron emission or electron capture. So another problem here, you can pause the video and work it out. Predict whether krypton 85, is stable or radioactive. If it's radioactive, predict the mode of radioactive decay and the daughter nuclei. So we have 85 is our mass. Krypton is number 36. That gets me 49 neutrons. We want our ratio, we're element number 36, so our ratio should be about 1.25 neutrons per 1 proton. If we take 49 divided by 36, we get 1.36. So we have too many neutrons. If we have too many neutrons, our solution would be beta emission. So we can take our 8536 krypton, emit a beta particle, and then we will get still 85 and now 37 rubidium. So there's our answer. Too many neutrons. Okay, magic numbers. So besides that neutron to proton ratio, the actual numbers themselves affect stability. And so more stable nuclei have even numbers of protons and neutrons. If your total number of nucleons adds up to what's called a magic number, the nucleus is more stable. kind of the same idea as noble gas electron configuration. So this is not something you have to memorize. It's just kind of for your own interest. All right, but we should talk about a decay series. We often get one radioactive nuclide that changes into another radioactive nuclide. So the daughter nuclide is also radioactive. And so what we get is kind of a cascade that's called a decay series, where we get radioactive nuclides produced one after the other until we hit something stable. So to determine where your stable nuclide is at the end, you can count the number of alpha and beta decays, and then from your mass number, subtract 4 for each alpha. From your atomic number, subtract 2 for each alpha and add 1 for each beta. So here's an example, uranium-238 decay series. Uranium eventually decays down to lead. You can see that there are multiple ways to get there. So it always goes alpha decay, 2 betas, and then several alphas. But then to get all the way down to lead, 206, there's a variety of ways that you can do it. But any combination that you do, uranium ends up down at lead.